All right, so today's notes are on inverse functions and relations. It's section 6-7. And our content objective is to find the inverse of a relation or function, and our language objective is to use the correct terminology to describe those things and how to solve for them. So first thing we're going to do is dive in and define what an inverse relation is. And I'm going to use the more jargony example first, and then we'll break that down what it means. So if a relation has an element of its domain, which we'll label A, paired with an element of its range, which we'll label B, then the inverse pairs B with A. So again, in simple terms, X and Y, or X, the domain, and Y are switched. So your domain and range switch with inverse functions. So if we're using the same letters that they use, the original would be A comma B, and the inverse, that's an arrow, the inverse would be just the reverse, B comma A. So again, inverse functions are just when you switch the X and Y's, the domain and range. So that's what an inverse relation is. An inverse function is the same thing. The only added component is that an inverse function or inverse functions are when both the original and inverse relations are functions. Are also functions. So they have the added element of not having any repeating X values. So that's our definition of inverse relations and inverse functions. But let's talk about what that means first graphically and then for our equations and domain and range. So we're going to start with graphing. So graphing inverse relations. If I have a graph and I'm going to do a sketch of a graph, I would recommend you sketch it so that you can actually see what points you're plotting, because the ones we're plotting are going to be demonstrating the point. So make sure you actually can see your dash marks and it's not a crazy thing. If you have a second color, that might be helpful as well. So in our original relation, we're going to use the coordinates 0, -1, 1, 0, and 2, 1. So if I plot those points, I have 0, -1 here, I have 1, 0 there, and I have 2, 1 here. So that's my original function or original relation points. I'm now going to sketch the inverse coordinates. So again, for these, all I'm doing is switching the X and the Y. So my first one would be -1, 0. The second would be 0, 1. And the last one would be 1, 2. So if I plot those points, I have -1, 0 here. I have 0, 1 here. And I have 1, 2 here. So my inverse points are, if you are right along here, the key thing to note is that they are being reflected over the line y equals x. So since your x and y's are switched, it makes, I think, some intuitive sense that they're going to be reflected over the line y equals x. So I'll put a little note here. So when you switch your x and y's, it's the same thing. This one is just switched to there, to there, to there. It's reflected over that line or flipped over that line. And that would be true of any inverse relation graphing. All right, so now let's talk about an actual equation and some domain and range things. So we're going to jump into some more of the nitty-gritty stuff. I'm going to flip the page for that. So finding inverse functions. I want us to consider the function f of x equals the square root of x minus 2. So that's our function equation, our original function equation. First thing I want to consider, and I'm going to do a few different parts building off of this original function, but the first thing I want us to consider in part A is what are the domain and range of the original. So what are the original domain of f of x? And so the first thing I need to do is I'm going to determine the domain. So what x values make the function real? So in this case, since I see that my function is a square root function, I know what is under the radical. Since it's a square root, it's an even root, I know x minus 2, that part under the radical, needs to be greater than or equal to 0. Because I know that I can't take the square root of a negative number and get a real answer, I need to find what values of x will make what's under the radical greater than 0. So if I solve out for x, I get x needs to be greater than or equal to 2. So my initial domain is going to be x is greater than 2. Then I'm going to do the same thing for the y values. So determine, or not necessarily what makes the function real, but what y values will result given my constraints on my x values. So determine the y values. I'm going to note you consider in this situation, we would normally do plus or minus any square root, but when we're graphing or considering functions, we're only considering the principal root, because we know then we wouldn't have a function if we took both plus and minus, because there would be 2 y values for every given x. So when we're talking about square root functions, we only consider the principal root. Okay, so in that situation, since I'm only considering the principal root or the positive root, that means that y would have to be greater than or equal to 0. So my y would have to be greater than or equal to 0 since I'm only considering principal roots, which means I'm only considering positive roots. That would be my range in that situation. So then, next thing, this is going to be probably the most important part of this lengthier example. So I want to know what is the inverse of this function. And I'm going to take a little side note and note the notation, because this is a common source of error. So in this notation note, I want to point out that f to the negative 1 of x is how you write an inverse function, and it is not an exponent. So you can write a function to an exponent, but it would be written differently. So if I have f to the negative 1 of x, it's an inverse function, but that is not the same as f of x to the negative 1. So these mean two different things. This means the whole function raised to the negative first power. This means an inverse function. These you won't deal with immediately. They'll maybe come up, or they'll come up later down the line in math, but not yet. This is an inverse function. So this is not an exponent. This is an exponent. So I want to be very clear about that. Make sure you do not write inverse functions this way. They are only written with the negative 1 between the f and the x, or between the g and the x. It is not written at the end. So those are two key things to keep in mind. Now back to the rest of the actual example. So in this case, I want to actually find our inverse function. So the first thing I'm going to do is write the original equation, but with y instead of f of x. So now my equation is going to be y equals the square root of x minus 2. Step 2, I'm going to switch my x and y values. So now I have x equals the square root of y minus 2. Then I'm just going to solve for y. So again, since inverse functions, your x and y are switched, that's how you're going to start solving for your inverse function. You're going to switch x and y and solve for y. So to do that, I'm going to get rid of that square root. So I'm going to square both sides so those cancel. And I get x squared equals y minus 2. Then I'm going to add 2 to both sides, and I get x squared plus 2 equals y. So then I can write my final inverse equation. F negative 1 of x is equal to x squared plus 2. And that is my inverse function equation. So now I know my inverse function equation. Pretty easy steps. You just switch x and y and solve for y. Those are the two key easy steps. Switch x and y and solve for y. But now I want to talk about what the domain and range are for this new inverse function. And this is pretty easy. You should double check this to make sure you did it correctly. But when you have the domain and range of the inverse, they're just switching the original domain and range. So my domain here is going to be the range of the original function. So x is going to be greater than 0 since originally y was greater than 0. And similarly, y is going to be greater than or equal to 2 since originally x was greater than or equal to 2. This also makes sense for our quadratic, for our range, because we know this would move it up 2. So our vertex would be at 0, 2, meaning y would have to be greater than 2. The only thing is we have to carry over this domain. So since our domain, the range was originally constricted to being greater than 0, our domain has to continue to be so in order for it to be the inverse function. All right, so the last little bit I want to mention for this example before I do one last key point is the inverse function a function? And in this case, yes, it is. So there are not going to be any repeating y values for an x value. So for each x value, there's only one y value. Again, it's a quadratic, so there's not any number I could plug in and get a duplicate y value. So it is indeed a function. All right, so I'm going to do mention one last key concept. So I'm going to flip the page to fit this in there. But one last key thing I want to note for these notes is combining sort of our composite function stuff that we did last lesson with the inverse function stuff. So key concept, if f and the inverse of f are indeed inverse functions, then we can say f of the inverse of f of x would equal x. And similarly, the inverse of f, or inverse of f of x would also equal x for the x in the domain of both, or domains of both f and the inverse of f respectively. So meaning it would have to be satisfying the initial constraints of the domain, then this should simplify to just x in either composite function situation. This, I think, should make some sense because obviously we know that they're the opposite, so they should undo each other. So it should simplify to the just simple value or variable of x when you do this. But to make sure that, or to sort of give a quick example of how it works, I'm going to use our last function. So we have f of x equals the square root of x minus 2, and the inverse of f of x equals x squared plus 2. So I'm going to show you that this indeed proves true with these two examples. So if I take f of the inverse of f of x, then that would be equal to plugging in this function to the original. So that would be the square root of x squared plus 2 minus 2. So if I'm going to simplify that and show you it indeed becomes x. Since there's nothing in front of these parentheses, I don't actually need them, so I know plus 2 and minus 2 are going to undo each other. So I'm left with the square root of x squared, which we know simplifies to simply x, so that one works. If I do the same thing with the inverse of f of x, then I'm now plugging in f of x into x squared. So I'd have the square root of x minus 2, that whole quantity squared, plus 2. Since I'm squaring a square root, I know those would undo each other, and I'm left with x minus 2 plus 2, which is just x. So that also proves true. So again, the last key concept is just that if you use composite functions and plug an inverse into the other one, it should simplify to just x. It's a good way to check your work. If you're not sure if you properly solved for an inverse function, you should be able to plug it back into the original and simplify to x. If it doesn't happen, you did something wrong. All right, make sure you write down any questions, comments, concerns you have on this stuff so we can go over it together in class.